Welcome back to the deep dive. Today we are taking what feels like an architectural X-ray to the very foundation of the digital world.
It's something we all use but rarely think about, right? The actual nuts and bolts.
Exactly. So think about everything complex your phone or your computer does. I mean, running massive AI models, processing gigabytes of financial data, even just streaming this audio to you right now.
hmm
We are stripping away all that, the apps, the code, the user interface, and we are looking for the single deepest idea that makes it all possible.
It's so easy to think that the complexity is all in the software. I mean, it's intuitive, right? You see a huge video game, you think about the millions of lines of code.
Absolutely. But what we learn, and this is what's so fascinating from the source material, these excerpts from The Atomic Architecture of Digital Logic,
Mm,
is that the truly foundational idea isn't that complex software at all.
no, it's shockingly simple.
It's physically simple, it's repetitive, and it's happening at a microscopic scale. The big idea is that all this complexity is built on, well, billions of tiny, tiny physical decisions being made every single second
Right there at the hardware level.
at the literal hardware level, and that's really our mission for you today.
Yeah, we want to give you a kind of shortcut to understanding that physical world that's living just beneath the screen.
The idea is that you'll understand that the most sophisticated software, from Face ID on your phone to these massive spreadsheets, it's all ultimately built from just three incredibly simple, interconnected physical rules.
Re-rolls, that's it.
That's it. And we are diving into the fundamental building blocks of those tiny decisions. The logic gates. Once you get this, you really unlock a core understanding of how computers decide.
Okay, so let's unpack that. What is a logic gate?
Right.
At its core, a logic gate is just a small circuit, a microscopic little component made out of transistors.
Yeah.
It is the fundamental physical unit of all digital computation.
So it's a physical thing. It's tiny. And it has one very specific job to do.
One unchangeable deterministic job.
Exactly.
And that job is defined by its input and its output.
Okay.
So a logic gate takes one or more inputs, and these inputs are strictly binary. In the world of computers, that just means they can only be a 0 or a 1,
On or off.
on or off. Physically, a 1 usually means there's a voltage present, electricity is flowing, and a 0 means there's no voltage, a low signal.
It's the simplest possible switch. True or false, yes or no. That's the entire alphabet.
That's the whole language.
Yeah.
And based on those binary inputs, the gate applies a fixed, unchangeable physical rule. And that produces a single binary output, also a 0 or a 1.
So this is where logic stops being an abstract idea and becomes a physical thing.
That's the insight, yeah. It's translating an if-then condition directly into electricity, either flowing or not flowing. It's logic made of silicon.
And it still feels, when you think about the internet, AI, everything, it seems a little preposterous that it could all be built on just three simple rules.
It does. But the source material is really clear on this. We're focusing on the three foundational gates that, when you combine them, can build literally everything in computing.
They are the atoms of logic.
That's the perfect term for them. They're like the primary colors of the digital world. Every single thing you see on a screen is just a combination of these base components.
And those three atoms are not SECI, AND, and OR. So our journey today is to explore these three simple rules, really understand what they mean physically, see how they chain together.
And then see how that chain leads directly to the blueprint of a CPU.
Let's do it. Let's jump into section 1, not AND, or the simple rules that govern everything.
So we'll start with the simplest one, not. It's often called the inverter.
The inverter.
Conceptually and physically, it's the simplest idea in computing. It only takes a single input, and it only does one thing.
And that one thing is
do the opposite.
the rule of inversion. It sounds so basic, but it feels like it must be absolutely critical for control. It's the only one that guarantees you can flip a state.
It is critical. It takes one input and just flips it. So if electricity is flowing in a 1, it guarantees the output's blocked. A 0.
And if no electricity is flowing in a 0,
It guarantees the output signal flows. It becomes a 1. There's absolutely zero ambiguity.
let's just state the rules explicitly because I think that really helps ground this. So if the input is 0, the output must be 1, not t0 equals 1.
Right.
And if the input is 1, the output has to be 0 to a 1, not t0 equals 0.
And you asked why this is so necessary. I mean, why do you need to be able to flip things?
Yeah.
It comes back to that idea of control. If all you had were AND and OR gates, you could only really start processes based on the presence of a signal.
Okay, right. A signal is here, so do something.
Exactly. But in the real world, you often need to trigger an action based on the absence of a signal. or you need to prevent something from happening.
Can you give us an example of that? A
Yeah,
scenario where not is the hero.
sure. Think about a safety system on a piece of heavy machinery. The main power is always on, right? So that's a constant one. But you need the machine to run unless someone presses the big red emergency stop button.
Right. You hit the button, the machine stops.
When you press that button, it sends a 1 signal. Now, you don't want that 1 to just go into the motor. That might not do anything. Instead, you route that emergency signal, that 1, through a NOT gate
Ah, so the not gate key is the 1.
and flicks it to a 0. That 0 then becomes the explicit off signal that shuts down the motor circuit. The absence of the stop signal lets it run. The presence of it guarantees it stops.
So the not gate lets the system handle contradictions. It allows for conditions based on both presence and absence. If signal A is active, signal B is forced inactive.
That's it. It's how you build control loops, which are fundamental for any stable system.
Okay, that makes sense. So let's move to the second foundational gate. This is where we introduce multiple inputs. The A and D gate.
Yeah, now we're moving from a simple action to the simplest possible decision involving two things. And the rule here is, it was very strict.
The A and D gate is all about both must be true. That's the concept.
Right. It takes two inputs, let's call them A and B, and it will only, and I mean only, output a 1 if both A and B are 1.
It's the gate of strict agreement, no exceptions.
And this is where we need to introduce what's called a truth table. It's just a simple way to map out all the possible inputs and what the output will be.
And for an A and D gate with two inputs, there are 4 possibilities.
4 possibilities, and the A and D gate filters them ruthlessly.
Okay, let's walk through that table so everyone can really internalize this. Possibility 1. Input A is 0, A and D. Input B is 0.
The output is 0, nothing happens.
Possibility 2. Input A is 0, A and D. Input B is 1.
Still 0. Input A failed the tests. The circuit is broken.
Okay. Possibility 3. Input A is 1, A and D. Input B is 0.
Again, the output is 0. This time, input B failed.
It's only that last final case. Possibility 4. If input A is 1, A and D. Input B is 1.
Then, and only then, the output is 1. The consensus is met. The signal goes through.
The source material used this great analogy of a high-security vault door.
It's perfect, isn't it?
It really is. You need
Okay.
key A turned and key B turned. One or the other does absolutely nothing. You need that simultaneous action.
And in computing, this is crucial for things like sequencing or making sure data is saved before you do something with it.
How so?
Well, imagine you're about to write a big file to your hard drive. You might have an A and D gate that needs 2 signals to be 1 before it proceeds. First, did the write command signal arrive? That's input A.
Okay, the user clicked save.
Right. And second, is the memory block available signal active? That's input B. If either of those is a 0, if the user didn't click save, or if the drive is full, the A and D gate outputs a 0 and the whole operation stops. It prevents data corruption.
What's so interesting is how unforgiving it is. 3 out of the 4 possible outcomes are 0.
Exactly. It's designed to filter out any uncertainty. It's the physical embodiment of a strict condition.
Which brings us to our third atom, the OR gate. And it's basically the philosophical opposite, isn't it?
Completely. If A and D is all about strict consensus, OR is built for flexibility, for redundancy.
The backup plan.
That's the concept. At least one must be true. It's designed to make sure that if there are a couple of different ways to get something done, any one of them is good enough.
So its function is simple. It outputs a 1 if input A is 1 or if input B is 1.
Or if both are 1.
Right. Let's run through the truth table for the OR gate just to see how different it is from A and D.
Okay, so scenario 1, if A is 0, OR, B is 0.
Then the output is 0. This is its only failure mode. No signal from anywhere.
Right, no power, no action. But scenario 2, if A is 0, OR, B is 1.
The output is 1. Success.
Scenario 3, if A is 1, OR, B is 0.
Also 1. Still success.
And finally, scenario 4, if A is 1, OR, B is 1.
The output is 1. And that's an important point you made. It's an inclusive OR. It doesn't care if both are true, just that at least 1 is.
So you have 3 out of 4 outcomes resulting in a 1. It's designed to succeed.
The backup plan analogy makes total sense now.
Let's go back to that data example. Say a program needs a piece of data. Maybe it can get it from the main network, which is route A, or it can get it from a local backup file, which is route B.
Okay.
If route A is working, it sends a 1. If route B is working, it sends a 1. The OR gate just needs one of those paths to provide a 1, and the whole process continues. The system is resilient. It can handle one path failing.
That's incredible. The need for robustness for a plan B is literally built into the physical circuitry.
It is. So now we have our 3 atoms, not for inverting, A and D for consensus, and OR for redundancy.
They seem so simple, but now we're at that big question. How do these three sort of basic ideas build a modern microprocessor?
And that takes us right into section 2. This is where we see the power of just connecting them together. The magic really is in the chain.
Right, because this is where I think anyone listening might be a bit skeptical. We've just gone over three very simple rules. How can that possibly build something that can, run complex physics simulations?
The simplicity is definitely deceptive because they're never ever meant to work in isolation.
They're designed to be connected.
They're designed for one purpose: instantaneous sequential connection. The key mechanic is that the output of one gate, that 0 or 1, immediately becomes the input for another gate.
Or for multiple gates at the same time.
Or for hundreds of other gates.
Yeah.
You chain them together in these vast, intricate networks, and that cascade of decisions is what creates complexity.
It's like having only 26 letters in the alphabet.
Exactly. With just 26 letters, you can write a shopping list or you can write a masterpiece novel. The letters aren't what's complex, it's the arrangement.
So by arranging these three logical operations, the source material shows that you get these emergent behaviors. Suddenly the circuits can compare values or add numbers or even store data.
It is genuinely astonishing that the difference between a simple light switch and a CPU isn't a different kind of component, fundamentally. It's just the sheer number of them and the incredible complexity of their arrangement.
Okay, so to prove this works, we have to look at a concrete example. How do we build something more complex out of these atoms?
Let's start with our first example, the exclusive OR gate, which is usually just called XOR.
And this one isn't foundational, right? It's derived. We build it from the others.
That's the key. It's built entirely from NOT, AND, and OR. And XOR has a very specialized job. It's often called the difference detector.
The difference detector.
Because it outputs a 1 only when its two inputs are different.
Oh, interesting. So if both inputs are the same, both zeros or both ones, it outputs a 0.
Correct. If A and B match, it shuts off. If they clash, it sends a 1. This is kind of nuance that you just can't get from a simple AND or a simple OR.
Right, because a simple OR gate would still output a 1 if both inputs were 1. XOR specifically does not.
And the beauty is seeing how it's built. How do we combine the atoms to enforce that rule? The logic is basically this. The output should be true if A is 1, A and B is 0, or R if A is 0, A and B is 1.
Okay, wait, let me break that down with the gates we just defined. We're saying take input A and feed it into an A and D gate with the inverted version of B, the NOT of B.
Yes, that little subcircuit handles the first condition. A is true, but B is false.
And then you build a second parallel circuit that does the opposite. It takes input B and runs it through an A and D gate with the NOT of A,
which handles the second condition. B is true, but A is false.
And then the outputs from those two parallel A and D circuits, you feed them both into a final OR gate.
Exactly. So if either of those unique conditions is met, the final OR gate outputs a 1. But if the inputs match 1 and 1, or 0 and 0, neither of those AND gates will fire, and the final output is 0.
That is the architectural blueprint. You've just created a brand new piece of hardware logic, a difference detector, just by arranging the atoms.
It's proof that you can create nuanced logic from simple rules.
But why is this specific function detecting a mismatch so important in computing? You mentioned error checking.
Yeah, error checking is probably its biggest job. When computers send data, especially over, a Wi-Fi signal or a long cable, a stray bit of electrical noise can easily flip a 0 to a 1, or a 1 to a 0. It's called a bit flip.
And XOR is how we catch that.
It's the primary tool.
Yeah.
So let's say you're sending a small chunk of data, maybe 8 bits. Before sending it, the computer runs an XOR operation on all 8 bits together.
Okay.
The result is a single bit, a 0 or a 1, and it's called a parity bit. That 1 bit gets tacked on and sent along with the original 8 bits.
So now you're sending 9 bits instead of 8.
Exactly. And the receiving computer gets those 9 bits and performs the exact same XOR calculation on all of them. If the data arrived perfectly, the final result of that XOR operation will be 0.
Why 0?
Because the original data, when XORed with the correct parity bit, should perfectly cancel itself out. There's no difference detected. But if even one single bit got flipped during the trip, that final XOR calculation will produce a 1.
And that immediately signals an error. It's just something's wrong here. Resend the data.
Instantly.
That's astounding. So that physical logic of difference detection is being used billions of times a second just to make sure the internet works reliably.
It's the digital chaperone. So we've gone from atoms to a functional molecule, the XOR gate. Now let's take the next giant leap that's in the source material, the point where this logic becomes mathematics.
The half adder.
The half adder.
We're going from logic comparison to actual arithmetic. This is the moment a computer learns how to be a calculator.
Right. A computer has to do math. And the smallest possible piece of math is adding two bits together. You can have 0 plus 0, 1 plus 0, 0 plus 1, or 1 plus 1.
And the half adder is the specific circuit built to do just that one simple operation. And the genius is that it's built using only the two gates we've just been talking about.
Just X, R, and A and D.
So how does that work?
Let's look at the only tricky part of binary addition, which is 1 plus 1. The answer isn't 2 because 2 doesn't exist in binary.
Right, the answer is binary 10, which means the sum for that column is 0, and you have to carry a 1 over to the next column.
Exactly. So the half adder needs two separate outputs for every calculation, the sum bit and the carry bit.
And this is where the gates just fit perfectly.
They fit perfectly. The XOR gate perfectly handles the sum output. Let's just look at the XOR truth table again, but think of it as addition. 0 plus 0 is 0. XOR gives you a 0. 0 plus 1 is 1. XOR gives you 1. 1 plus 0 is 1. XOR gives you 1. And here's the clever part. 1 plus 1 is 0 with a carry. XOR gives you 0.
The XOR gate literally computes the sum bit for all four possibilities.
It does. And what about the carry bit? Well, that's handled by the A and D gate. When do you need to carry a 1?
Only when you're adding 1 plus 1.
And when does the A and D gate output a 1? Only when both inputs are 1.
So for 0 plus 0, 0 plus 1, and 1 plus 0, the A and D gate outputs a 0, no carry. But for 1 plus 1, the A and D gate outputs a 1, the carry bit.
And there you have it. By combining an XOR gate for the sum and an A and D gate for the carry, you have physically constructed the most basic elemental machine capable of doing math.
That is the absolute foundation of all digital mathematics. And of course, this leads to scaling it up. A half adder is great for 2 single bits, but our computers work with, 64-bit numbers.
That's the next step. The half adder is a little limited because it can't accept a carry bit coming in from a previous calculation. So engineers use these gates to build a full adder.
And a full adder can handle 3 inputs.
3 inputs, input A, input B, and the carry-in bit from the column before it.
So to add 64-bit numbers, you just chain 64 of these full adders together.
You chain them together, and that structure is the heart of what's called the arithmetic logic unit, or ALU.
The ALU, that's a term you hear all the time with CPUs.
The ALU is the mathematical brain inside the CPU. It's just a massive, complex arrangement of these logic, circuits, adders, subtractors, comparators. When you hear about the speed of a CPU, you're hearing about how fast billions of these tiny logic gates, organized into an ALU, can flip their states.
So the hierarchy is crystal clear now. The atoms not AMD or combined to make specialized circuits like XOR and full adders. The full adders are chained together to make the ALU, and the ALU, along with memory and control units, forms the CPU.
And it just confirms that the power of modern computing comes from the architectural genius of arranging these 3 simple atoms in more and more complex patterns.
And to connect that back to you, the listener, the next time you hit sum on a huge spreadsheet, what you're actually witnessing is the physical reality of thousands of these full adder circuits, cascades of XOR and AND gates, all firing at once to give you a result. It's physics executing logic.
Flawlessly and deterministically.
So we have to address the big question that always comes up when we talk about hardware. If it's all just zeros and ones flipping around, where does software fit in?
Right. Where does my operating system or my favorite app fit into this physical picture?
This is section 3, the great translation: hardware, software, and state flipping.
A really helpful way to think about it is with an analogy. Software is like a giant story. It's written in a language that humans can understand, like Python or C++.
And that story has the plot, the characters, the algorithms, the user interface. But a transistor can't read a story.
It definitely cannot. The CPU's job is to take that story, once it's been compiled down into raw machine code, and translate it into an...
Let's make that really concrete with those real-world examples again. Face ID. When my phone unlocks, I see the sophisticated biometric scan.
At a high level, yeah. But at the machine level, your phone's camera captures your face and instantly turns that image into a huge array of zeros and ones, billions of data points.
So my face becomes a massive binary number.
It does. And that data is then fed into a massive chain of comparison circuits, mostly XOR gates, or difference detectors.
And they're just comparing the new data, my face right now, to the stored data, my face from when I set it up.
And that comparison is physical. Bit by bit, the system is asking, does this new input bit match the stored bit? If it doesn't, the XOR gate for that bit outputs a 1. a mismatch.
And if too many of those XOR gates output a 1, meaning my face is too different.
The whole process fails. The final A&E gate in the chain, which requires consensus for verification, is denied a 1, and the phone stays locked.
But if the input data is close enough to the stored map, almost all the XOR gates output a 0. That consensus allows the final A and D gate to fire, outputting a 1.
And that single 1 is what the system interprets as Face ID verified. The unlock command is just the result of one A and D gate finally getting the all clear.
It's not magic, it's just massive, ridiculously fast physical comparison.
The same exact principle applies to the spreadsheet we were talking about.
Right, running a huge pivot table, it's doing millions of additions and lookups.
When you hit run, the software activates the ALU, the engine of adders. But it also activates the memory circuits, which are built from gates called flip-flops.
Wait, so memory itself, the ability to just hold a number, is also just an arrangement of not A and D and OR gates?
Yes. A single bit of memory is just a handful of gates chained together in a clever loop that can be set to hold either a 0 or a 1, and it will stay that way until a control signal tells it to flip.
So running that pivot table is just the CPU cycling through 3 steps over and over. Retrieve data from the storage gates, process it through the ALU gates, and write the result back into the storage gates.
That's the loop.
It's just, the simplicity of it is what's so beautiful. The entire complex digital world is governed by this hidden, simple physical architecture.
Which brings us perfectly to section 4. Because once you accept that the system is fully deterministic and built on these simple rules, it has some really deep philosophical implications.
Right. The logic gate structure gives us a really profound insight into what we even mean when we say a machine is intelligent. The source material is very clear on this. Computers don't understand anything.
And that clarity is so important because the whole system is built on these non-negotiable physical rules. A computer only ever transforms inputs into outputs. That's all it does. It's a perfect mechanism for executing logic.
It has no idea why it's doing it. It just knows that based on the laws of physics and the way the circuit is designed, if it gets an A and a B, it must produce a C.
Exactly. A logic gate doesn't know the difference between a 1 that represents the solution to a rocket trajectory equation and a 1 that represents a cat video successfully uploading. To the gate, it's just voltage.
Which clarifies where the meaning comes from. That's the key takeaway here, isn't it?
The meaning, the context, all of that comes entirely from us. We are the ones who took a complex human problem like facial recognition and painstakingly encoded it into the language of zeros and ones.
And we're the ones who then interpret the final binary output, that single one from the Face ID circuit, and give it the meaning, you are now allowed to use your phone.
It creates a really clean separation. Human intelligence deals with meaning, context, and abstraction. Machine capability deals with speed, scale, and flawless logical execution.
The machine is the perfect tool for executing our logical commands.
And this raises a really interesting question about what it means for a computer to fail, to crash, or give a weird result.
We always say the computer crashed or the AI made a mistake.
But you look at the lowest level. The A and D gate didn't suddenly forget its rule. It didn't decide that 1 A and D1 now equals 0. The physical laws were executed perfectly.
So if the final output is wrong, it means the flaw wasn't in the execution, it was in the instructions we gave it.
It was in the chain of logic we designed. The bug is always in the story we wrote, not in the grammar of the language.
A system failure isn't the machine failing to understand. It's the machine perfectly executing a flawed set of instructions that we wrote. It just reveals the error in our own thinking.
It puts the responsibility right back on the programmer and the architect, which is a pretty profound thought when we start talking about things like self-driving cars or medical AI.
Let's use this moment to just recap that ultimate takeaway. By understanding how these 3 simple rules, not A and D or function and connect, you have basically grasped the foundational architecture of the entire digital world.
It's why atoms of digital logic is the perfect name for them. We've seen how you combine them into molecules like XOR and then into complex structures like the ALU, and that's how you build this incredible machinery. Every single thing your computer does starts with a switch flipping or not flipping.
And understanding that is the key to grasping both the limits and the incredible potential of this technology. Every new algorithm still has to run on those billions of tiny, simple decisions.
Okay, that was a truly foundational deep dive, a journey to the microscopic heart of decision-making.
Yeah, we really charted the whole path. We started with binary input-output and defined the 3 logic atoms, not AAA and OR.
And then we showed how you chain them to create more complex functions, like the XOR gate, that difference detector that's so crucial for error checking.
And then came that huge leap where logic became mathematics with the half adder. We proved that the most basic function of a calculator is just a clever arrangement of XOR and AD gates.
And crucially, we tied it all together by explaining how software, no matter how complex the story, ultimately just translates down into patterns of these gates flipping states inside the CPU.
And the source material really points us toward the next logical step. We've talked about instantaneous calculation, but how does a computer remember things? How does it handle sequence and time? Right. We've covered addition, but a computer also needs memory and control.
Exactly. So the next deep dive would have to be connecting this logic to how these gates are arranged to create circuits that can store information, those flip-flops we mentioned, and circuits that can control the sequence of instructions.
And that knowledge would complete the blueprint. It takes you from a simple adder to a fully functional CPU that can manage and retrieve information over time.
It's the next layer of the architecture.
Fantastic. That's definitely where we'll go next.
Yeah.
And before we sign off, we always like to leave you with one final thought to chew on based on everything we've uncovered today.
So if we accept this premise that a computer only ever transforms zeros and ones according to precise physical rules, and that all meaning is imposed by us, the programmers, it leaves us with a final provocative question. When a complex system, like the AI in an autonomous vehicle, produces a catastrophic or an unintended result, does the machine ever truly fail? Or does it only ever flawlessly execute the logic it was given, perfectly revealing the profound flaws and the gaps in our initial encoding of the real world?
Meaning the machine is never wrong. We just asked it the wrong question. That is definitely something to think about. Thank you for joining us for the deep dive.